Yeah, good evening everyone. Switch on your camera. Let's start. The last thing we did was equation of continuity and streamlines. Hope everyone went through this. And I think we wrote down these equations. So the next part, like I said last time in Bernoulli, we have four concepts: velocity of a flux, aeroplane wing, venturi meter, and siphon. So the first part and the important one is the velocity of a flux. So what is this exactly? Consider a container with a hole of area A. So if you have a container like this, with a small opening like this. So this area of this hole is A. The area of the container is capital A. And let's say it is completely filled with liquid. The height is H. So this liquid will start rushing out, right? So this speed is called velocity of efflux. So the speed at which the water comes out of the hole is called velocity of efflux. Okay, so how do we calculate this? So we use the Bernoulli's equation, the equation of continuity. Let's look at this derivation here. So the thing, right? This is how the streamlines are coming out. This is how the streamlines are coming out with V. You're getting it? So all of them are forming this kind of a cone kind of structure here, and all the streamlines are coming down. Let this liquid come out with the speed V2, and let this liquid come down with V1. So let the liquid level decrease with speed V1. So here we'll consider this is state 1 and this is state 2. Bernoulli's equation is exactly like conservation of energy. You have to just define your states and apply the equation. I'll use the base as a reference. And this height is H. The first equation. This area is A and this area is A. No? A into V1 is equal to A into V2. Equation of continuity. Agreed? The liquid coming down is equal to liquid going out. Next thing, Bernoulli equation P1 plus rho G H1 plus half rho V1 square is equal to P2 rho G H2 plus half rho V2 square. So what is P1? P naught. Why? Because it is exposed to atmosphere top surface. Rho G H, that will be H half rho V1 square. What is P2? P2 is also P naught, no? Because the point 2 is just outside the hole. So the pressure is still P naught only. Height will be 0 because the reference line and half rho V2 square. P naught will cancel. From here, V1 will be AV2 by capital A. Substitute that here. Rho cancels off everywhere. So we get V2 is equal to root 2 GH by root over 1 minus A square by A square. This is the velocity of the liquid which is coming out. Small a is the area of the hole and the capital A is the area of the container. If the hole is very small, if A is much greater than A, there is a small hole then we can write A by A will tend to 0. Then the velocity of Fx, the formula becomes root 2 gh. What is h here? H is not height of the container. H is the height of the liquid above the hole. Have a look at this. So use the formula root 2gh directly if the hole is very small, right? If the hole is not small, you have to use that formula root 2gh 1 minus a square by a square. So 2006, now, when I gave the exam, they gave you the question like this thing. They said the area of the container versus the area of the hole, the ratio is 1 by 50. They said A by A is 1 by 50. So everyone assumed that the hole is too small. So kya farak padega? People use root 2gh. Even I did root 2gh, I got answer 49.5. And when I looked at the options are 49, 49.5, 50 and 50.5. They are just too close. Somewhere I was suspicious and said, let me use the actual formula, and the answer was exactly 50. So if they give you the area of the hole, there is a reason. If they don't mention small hole, and if they give you the area, you have to use a big formula. You can copy down this formulas and have a look at this, how we did this. And based on this, I'll give you a variations of this thing.
So in this will kept temperature constant.
Obviously, Naresh, yeah. What are you talking? Where is how will temperature change here? बताओ. यहाँ पे एटमॉस्फेयर है, यहाँ पे एटमॉस्फेयर है, टेम्परेचर कैसा चेंज होगा? क्या बात कर रहे हो? वही बोल रहा हूँ तेरा ना, यू ओवर थिंक इन द एग्जाम में वही करते हैं ना, यू ओवर थिंक अबाउट द क्वेश्चंस. टेम्परेचर कैसा चेंज होगा यहाँ पे? Check it out, everyone. Put down the formulas. Abhiksha, your cam is not working. I can't see you. Why so many people are missing today? 5 people are missing. Reina is gone out. Remaining people, I don't know. What happened? Some festival or something?
Vacations maybe?
I don't know what vacation. आज कुछ तो है गौतम बुद्धा का फेस्टिवल. People are celebrating गौतम बुद्धा का फेस्टिवल. People are Buddhists. Then it is fine. But I don't think anyone in the class looks like a Buddhist. We all look pretty violent, actually. None of you look like Buddhist type people here. If it is someone who has to be Buddhist, it is a innocent physics teachers like me only. Shaurya can be Buddhist, quite possible. Shaurya, Geet. Our main Buddhist Raina is not there. She went to somewhere to Rome. She is a proper Buddhist. Even during the class, everyone is feeling sleepy and tense. She's sitting and eating ice cream seriously. So that is the calmness of the mind. If you see, that is what Lord Buddha said, if your one of the leg is burning and the other leg, right, is in comfort. Doesn't matter, both are equal. The Reina is like that. Even under that constant pressure and tension of the class, still she keeps eating ice cream. So, yeah.
So, or maybe like today it's a lunar, there's a lunar eclipse today, so that's why people are missing.
People have not come. No, Vrinda is finding out new reasons. So let's assume people have just not come. Let's not find out the reason. You guys are still fine. You should ask the medical people. They'll give super reasons. They are quite weird. Clear with this thing? So let's see some questions on this. So the idea is pretty simple. So the water comes out. That's what we call a velocity of flux. So let's say you have a container and you made a hole here at a distance x, small hole. And this is h. So when you make a hole, what will happen? The liquid will fly and fall here. This is your range. Find x for maximum range. So where should I make hole in the container for the maximum range? Try. Easy one. What is the velocity when it comes out?
Under root 2gh minus.
So velocity will be root 2gh. H is the height above the liquid. Be careful. So you should take this height here, h minus x. What is the time of flight? Root 2x by g, na? Remember, it's like a thrown from a building horizontally, root 2h by g. So what is range? V into t. So this will be 2 into root over h minus x into x. So we have to maximize this function. So d by dx of hx minus x square ka differential. H minus 2x is equal to 0, x is equal to h by 2. So you have to make the hole at the center. So if you look at this container here, actually, if you make a hole here, and if you make a hole here, both will give you the same range. If you take from the top or if you take from the bottom. So if you make a hole from the top at distance x, or if you make a hole from the bottom x, the range will be same. Because logically kya hoga na? This h minus x and x will get interchanged, na? If the hole is on the top, what will happen? Speed is less, but time is more. The hole at the bottom will have more speed but less time. End of the product will remain same. So the two holes at a equidistant from the both the sides will have same range. Remember, container is on the floor. Clear? So here, this is a better version of this. You can remember the result. What if you have a container placed on a platform? Let's say this is H1 and this is H2. So the hole, na, for maximum range, this is the condition. Let's say the hole ka distance is x from the bottom. For max range, it should be the midpoint H1 plus H2 by 2 if x is greater than H2, or the answer is H2 only if x is less than H2. What is the meaning of this? Let's say we have a container like this. Let's say this height is 2h. This height is h. So where is the midpoint? 3h by 2, no? But what if you have a container like this? Now where is 3h by 2? 3h by 2 is here, no? Is there any container there? Container hai hi nahi. So water won't come only. So what is the best point that you can have? The bottom, right? Getting the answer, what I mean to say? When you take the midpoint, if there's a container, then it is fine. If there's no container there, then the lowest point of the container is the answer. valid for where is rho in this formula? Sir? There's no rho anywhere, na Shaurya. So why does it matter? Formula में rho तो है ही नहीं. All clear with this? Let's say we have a container here filled with liquid. Height h, area A. This is placed on a platform. This height is also h. And at some distance here, you kept a small bucket. This distance is also h. And this distance is h by 2. So now what happened? You made a hole at the bottom. This is a small hole. What will happen? Initial liquid will fly, na? Water level decrease hoga. As the water level decreases, what will happen? The liquid will start falling like this. Isn't it? As the water level decreases, the liquid the range will keep decreasing. So as water level decreases, range decreases. So the question is, how much water is collected in the bucket? So we have a bucket of width h. As the water level decreases, range decreases. That means some part of the water fell into the bucket. How much water is collected in the bucket? Got the question?
Sir,
बोलो ना.
sir, is it like that question in kinematics in which we did पानी boat में जा रहा है?
वो stone throwing वाला ना.
हाँ,
ठीक है ना.
minimum
If you think that is the answer, करो ना. Then who's stopping you? Did everyone got the scenario? The end of the day, some water will get collected here. So how much water gets collected in the bucket? There is no need to use any integration or difference. कुछ नहीं. You'll get it without integration. Try how to do that. Can I say like this? See, let's say when the height is certain height, this will come and fall on this edge. Agreed? So range, you know the range. From there, can you find the speed? And from there, can you find the height? Similarly, at a certain height, it will just fall on this corner. That means all this water is in the bucket, na? Are you getting the logic there? You can find the height when the water falls on this corner. You can find the height when it falls in this corner. But the difference in height is there in the bucket only. Try. I'll give you a minute now. So see, let's find this height when the water comes and hits on this corner. Let's find this height when the water comes and hits this corner. Let this height be h2. Let this height be h1. So when this is coming, the velocity will be root 2g h2. When this is coming, the velocity is root 2g h1. So for first h2, what is the range? 3h by 2. What is range ka formula? Velocity into time. What is velocity? Root 2g h2. What is time? Root 2h by g. That is constant, right? Time of flight is same all because the water will always come from this point only. Gg will cancel, square on both sides. 9h square by 4 is equal to 4h h2. h2 will be 9h by 16. For h1, range will be h by 2. That will be root 2g h1 into root 2h by g. h1 will be h by 16. You're done, right? So the water in the bucket will be area into h2 minus h1. h by 2. Half of the water will be in the container. Easy? We just used kinematics. No need to integrate. कुछ करने का जरूरत नहीं. Clear? Next thing. Any doubts on this? We have a container filled with liquid. Area is A. This is a small hole, but area is smaller. So if I use the word small hole, you can use root 2gh. And the liquid is coming out. Initially, the height is h. Find the height of the liquid as function of time t. So the water is leaking out. So what is the height of the liquid as function of time t? So simple question will be, after what time will the tank become empty? Or they can even ask you like, find the ratio of time taken for the first half to be empty and the second half to become empty. Which one will be more, first half or second half?
First half time would be less.
Yeah. Initially, water will go fast, na?
Yes.
Upper half will leave fast, second half will go slow, right? Upper ka tank खाली हो जाएगा fast. How will you find the time, people? Find the height as function of time t. Get it? All these are standard models and good ones. Try it and I'll give you a minute. Mm-hmm. This involves integration. Let the height be x, okay? So let the height be x at some time. So in time dt, let liquid level drop by dx. So in that small time dt, right, this much amount of liquid went out. So that is only this thing, no? So how much liquid went out? A into dx. This is the outflow. This should be equal to how much? This is going with speed v and area A. That is nothing but, remember, outflow per second is how much? The flow rate basically. Outflow per second is area into velocity, no? So in time dt, how much flows out? A into v gives you how much liquid flows out every second. In time dt, your A into v into dt is flowing out. Put a minus sign because x is decreasing. This is equal to AV dt. So basically the liquid level decreasing. This is the liquid outflow. Make sense? Whatever decrease in the container should have gone outside. Minus sign because it is decreasing. So we get minus A into dx. What is the velocity? Root 2 gx. There, that's it. One integration step. Initially height is h times 0, x and t. This will be 1 by root x, na? X power r, so 2 root x. Limits will be h to x minus a by a root 2g time. Ye important formula. So root x will be root h minus a by a root g by 2 time. You can work up this formula. Straightforward question you get in the exam. Find the time when the tank becomes empty. Put x is 0. Find the time when the first half is empty. Put x is h by 2. So put x 0, put x is equal to h by 2. You'll get the time for first half and the total time. Subtract karo, second half ka time aa jayega. Right? Find the time for the full time to be empty. Find the time for first half to be empty. And if you subtract them, you'll get second half to empty time. Put it on. The result is important.
So
You
full
need to
time
mark it up.
x equal to h.
X is equal to 0, right? X is the
Okay.
yeah. Do check it out. Clear? Any doubts on this derivation? Please ask. Let's see. This is a good one, right? So someone made a bowl. The previous one, actually, right? I can make a variation of this question 34 kana. Let's say we have a container with a small hole. Area A. And here you have a water ka tap. So water is falling inside. So the water is falling at a rate of, let's say, meter cube per second. Initially there's no water. And A is the area of cross section. Okay. So what will happen? Water is coming inside also, water is leaking also at the same time. Can you tell me roughly what will happen eventually? If they ask you a simple question, which of the following is the graph for height versus time graph? If they ask you to draw the graph for height versus time graph, कैसे दिखेगा? Can someone guess? Or if they ask you find the final height, that will be simple mains and bits level question. How will you do that? Find the final height.
It will be like it'll be almost flat at the start and then grows exponentially.
Is it go to infinity finally?
A bit slower than that, actually. Like after some time, it will.
Actually, socho na. The liquid that comes out, uska speed v is root 2 gh. Where h is the height of the liquid that is already present. Initially, kitna tha? 0. That means whatever is coming in, but nothing is going out na initially. So inflow is more than outflow, isn't it? As the liquid height is increasing, more and more liquid will go. At one point, the height has increased so much, whatever is coming, everything is going out. Isn't it? So the height, right, would actually increase, and eventually try to become a constant value. Is that making sense, Rishi?
Yeah. Makes more sense.
You're getting it. Initially, there's no water only to go out. Na? Where it will go? As the water is getting collected, as the height increases, more and more water goes out. You're getting it? You can try this.
I think I was thinking like
you're saying this
flip.
only, but you got confused. You can try in your sink in the bathroom. Open the water tap and see. Initially, it fills up. At one point, the water does not increase the level anymore. Whatever is coming from the tap, everything goes through the sink. Because once the height increases, the speed of outflow will increase. So more and more water is leaving out. So if they ask you the final height, that is an easy question. Let the final height be h. So outflow will be a into root 2 gh. That should be equal to q. So आ जाएगा एक step में answer. Isn't it? Inflow is equal to outflow. That will be a final height. But anyway, if I want ask you to calculate this problem, right? This is how we do. Let the height be x.
So like steady state, no?
ये steady state नहीं है. It is increasing here, no? So here I'm trying to find a function of time. That is steady state, finally steady state.
Okay.
So here the rate of change of flow will be how much? So inflow will be q minus a into root 2 gx dt. So this is inflow from the tap. This is outflow from the hole. The balance will be a into dx. Is this making sense? whatever water came inside, that will be Q into dt. Whatever water went outside should be equal to the height increase, ADX. So this will be dx by Q minus A into root 2gx. If I make Q is equal to 0, it becomes the previous question. Is equal to dt. Integrate 0 to t, 0 to x. This will be a minus 1 by a. इसका integrate करना पड़ेगा. I will leave it there, but I hope you got the point. 1 by root x का integration it is. You can put q minus a root 2gx is equal to dt and integrate it. Clear? Got the steps right? So there, physics part is over. Then it is just a little integration involved. You can just put z is equal to q minus a root 2gx and get it. So dg will be a root 2g 1 by root x dt. Okay? From there you will get the answer. So that is the same thing, but a better variation of this. But yeah, if they ask you this thing, so final height will be inflow is equal to outflow. That could be a simpler question. So inflow is Q, outflow will be A into root 2gh. And if you plot the graph, height versus time, this is at h max. That is how the height will increase and eventually reach the maximum value. All clear with this? Next thing. This right is another question. Let's say someone made a bowl. We have a small hole here. Area A. In this bowl ka equation, na, y is equal to k into x power n. That is a bowl ka equation. Actually, we can find the bowl ka equation. Let's say there's a liquid here, and the liquid is leaking out. And we observe something interesting. We observe the height of the liquid decreases at a constant rate. Think about it. Normally, when you take a cylindrical tank and if you make a hole, initially water level will drop fast and then it will slowly decrease, na?
Yes.
So the height won't increase at a constant rate. The height of the liquid falls at a constant rate. Okay? So find the equation of this bowl. This is an integer question. The equation of the bowl is equal to k into x power n. Find n. So this happens for a particular shape. So this is a very special bowl. No matter how much high you have, the water will fall at a constant rate. No रे शौर्य, you're guessing. I understood. Solve कर. हर बार parabola नहीं होता life में. How do we proceed with this? This is a good one.
Sir, V equal to under root 2gx वाला formula was for that cylinder type. ना?
Come again.
V
Y is
equal
equal to omega square x square g वो.
नहीं V equal to under root 2gh और x वाला जो formula हमने derive किया.
देखो ना, V is equal to root 2gh में what is h? Height above the liquid.
हाँ.
Do I care what shape it is?
अच्छा no.
You don't care. The h is the height above the liquid. Done discussion हो गया. Whatever is the shape. So see.
Okay.
Let's say in time dt, story is still the same, people. In time dt, how much is flowing out? A V dt, agreed? In that same time, the liquid level here is dropping by this much. Let this coordinates be x comma y. So this is the origin 0 comma 0. This will be x comma y. So for this cylinder, what will be the radius here? So what you get is a small disc, na? Radius will be x and the thickness will be dy. इसका volume कितना था? Pi into x square into dy, right? This is the volume that decreased. That should be equal to this. This is the outflow. So pi into x square dy is equal to a into v into dt. But what is the velocity? Root 2 gy depends only on the height. So this will be pi into x square dy by dt. What is dy by dt? You said this was constant. The rate of change is equal to root 2 gy. Square on both sides. You get pi square x power 4 dy by dt whole square is equal to 2 gy. Y is proportional to x power 4, no? It's an x power 4 function, people. It's not a parabola. Check, there's no need to integrate on anything. Direct inflow is equal to outflow. So the equation of the bowl will be y is equal to that constant into x power 4. Check everyone.
Sir, because it's for small holes, you removed A, right?
Yeah. Because it is small hole, or else it will be quite messy. Because that capillaries will keep changing, no?
Sir, but just in case we had not removed the A, couldn't we just treat it as like a constant?
Constant नहीं होगा ना रे. That A will be pi x square, ना उसमें भी x आ जाएगा अंदर.
हाँ
ये फॉर्मूला क्या हो जाएगा? रूट ओवर 1 माइनस a by ये pi x square का होल स्क्वायर आएगा वापस.
हाँ.
It will be pretty messed up result actually. X power 4 जैसे नहीं आएगा, you get something else. All got this? Easy one. If you see, all these questions are 2-3 steps, but they're different. Any doubts on this thing? Labdi, Anamai, clear? Ritam, Nishita? Got this? Who is missing today? Ammu is missing also. Many people are missing. Gauri is missing. Reina is missing. 3 people are gone. Kavya is also missing. Kavya is there. Next one. Now, this thing, right? There's a variation of questions, but before that, let me show you something else. We have a container here filled with liquid. And you have a small hole here. The whole setup is rotated with omega, length L, density rho, neglect gravity. So basically here the pressure is P0. Find V. So we have a test tube which is rotating with omega, and suddenly there's a small hole at the bottom there. The liquid will start splashing out. Find the speed with the liquid comes out.
Sir, small hole is where at the bottom.
Yeah, bottom मतलब भाई ये corner पे दिख रहा है ना diagram.
Okay.
How do we do this? Do you remember that pressure at the interface का formula? You have done this. Pressure on an interface. I told you remember the result. अगर वो result आया तो question get in one step. Try, think for a minute. See, idea is pretty simple. Huh? So we will take a streamline just before and just after. Okay, we are taking this point 1 and this point 2. Remember the formula? Px minus p axis is rho omega square L square by 2. Rho omega square x square by 2. In case someone doesn't know what is Gajini, it's a movie where this guy keeps forgetting every 15 minutes. American ka movie hai na? That thing. So we call it Gajini basically. Got it? So this is Px will be, so pressure at point 1 will be, axis is P naught, rho omega square L square by 2. So apply Bernoulli between 1 and 2. So P1 plus rho g H1 plus half rho V1 square is P2 plus rho g H2 plus half rho V2 square. P1 is P naught plus rho omega square L square by 2. Height is same, 0, both will cancel. Half rho V1 square, we neglect this because A into V1 plus A into V2. V1 will be A by capital A, V2. This is almost 0 since the hole is small. P2 is again P naught plus half rho V2 square. P naught will cancel off. You end up with V2 will be omega square L square root omega L basically. You getting omega L. Cool answer. Clear? Remember, this is actually the radial velocity. Yeah? Meaning, if you look at the top view, the water jet which is coming out will have this speed V and will also have this speed na L omega. So the water is actually coming like this. Got it? The water is spraying out with L omega, but since it is going in a circle, it also has a tangential velocity. So we can have a general result for this for multiple liquids. So let's say we have a container rotating with omega. Let's say we have rho 1, x1, rho 2, x2, so on till rho n, xn, and the hole is made for rho n here and the liquid is coming out. This velocity v is given by omega into root over rho 1 x1 square minus 0 square plus rho 2 x2 square minus x1 square plus so on rho n xn square minus xn minus 1 square by rho n. This is a general formula if there are n liquids of n columns. So we did a very simple case where, rho 2, rho n all are 0, rho 1 and x only are there. So all these terms got cancelled, rho also get cancelled, you got just omega into x1 directly. But this is a better formula if you have n liquids. Idea is the same. We have to find pressure, like, we use the p axis minus that pressure here, 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 here. We add all the pressures and get it. Put it up. So this idea, right, finding pressure just before the hole will actually make your life easy. We have some models on that I'll show you, but ask me if you're confused anywhere here.
So can you go to the last slide, one? Done.
Sir,
Hmm.
if the pressure at the last is less than atmospheric pressure, then it won't go.
Why it will be less, Ray? Rotate हो रहेगा और centrifugal force is pushing it, pressure हर बार ज़्यादा ही होगा.
Acha, okay.
Now see, look at this thing. Based on this, we can get even a good question actually. Suppose if you have a container, let's say it is filled with different layers of liquids. Let's say this is one layer here. This is another layer here. Let's say this is rho 1. This height is h1. This is rho 2. This height is h2. So they'll ask you like this question. Then there is a hole here and the liquid is coming out. So just now, if you saw what we did, we took this point here and this point here. So end of the day, what you're doing is you're finding the pressure difference between 1 and 2 now. So velocity of efflux is simply root over 2 times delta P by the rho of the liquid which comes out. Where this delta P is the difference in pressure inside and outside the hole. Because end of the day, what you're interested in is the pressure difference only. Look at this result, how we got. Did you see end of the day, what you got is height is cancelled. This is cancelled. You got P1 minus P2, na? Isn't it? End of the day, the formula came as if it's a pressure difference only. Means all that height, velocity, all and I don't care. Inside and outside the hole. So in our scenario, the delta P will be, what will be the pressure there? So you have the pressure is P naught. Here the pressure is P naught plus rho 1 GH1. The pressure here will be P naught plus rho 1 GH1 plus rho 2 GH2. No? So the velocity of the efflux for this formula will be simply 2 times the difference in pressure outside is P naught. Rho 1 GH1 plus rho 2 GH2 by the liquid which is coming out is rho 2. Easy. same question I could have asked you like this also. You have a container filled with liquid here. Someone kept a piston here. Mass M. And area A, and this is rho, and this is height H. And the liquid is coming out. Again, see, same logic here. What is the pressure here? P naught plus the weight by area. What is the pressure here? P naught plus the weight by area plus rho GH. Outside the pressure is P naught. So here the formula velocity of F flux will be root over 2 times pressure difference. That will be P naught plus mg by A plus rho GH, that is the pressure inside, minus P naught by rho. Easy? So these are all the different variations of questions that will come. So just find the pressure at the bottom as if the liquid is not flowing, get the pressure difference and finish it off, 2 delta P by rho. So I can play around with different questions like this. I can even ask a question like this. We have a container filled with liquid, you closed it and you pumped air inside and pressure became 4P naught. Then they'll ask you what is the speed. So 4P naught plus rho GH minus P naught 2 delta P by rho. Are you getting this logic, everyone? Do check it out. Huh? This is a pretty good result actually. 2 delta P by rho. Doesn't matter whether you put multiple liquids, you put a block on top of it, you keep increasing atmospheric pressure, do anything you want. That thing works. Please look at the steps.
So means if there are 3 or 4 liquids, then also it can be valid.
हाँ. Add करते जा ना. mg by A, if you keep a block on the top, ना pressure क्या हो जाएगा नीचे? This is P naught into area, and this is mg, ना? Right, Arish? So P naught is there, plus ऊपर से mg is there. So, any doubts on this thing? Please ask me, people. So this general formula you can use this, and it works out. Clear?
So this came from the last one only.
Yeah. Idea तो वही से था. We are just extending it to multiple things. Next one. We have a container.
So can you show the formula once? Yes, sir.
The entire inside is filled with helium gas. Temperature is, let's say, 1000 Kelvin. This whole container is insulated. Outside is vacuum. So what will happen? The gas will start leaking. Right? So the question is, what is the speed of the gas initially? So outside vacuum, you can take it as 0 Kelvin. यहाँ पे temperature change होगा शौर्य. So the gas is expanding into the vacuum. Assume there is no flow inside the liquid. मतलब inside the container, assume the air is not flowing anywhere. Neglect flow rate inside the container. So find the speed, it comes out. Find the speed of the gas initially. Now we have to use that modified Bernoulli equation. Because when the gas comes out, temperature becomes 0 Kelvin, it cools down. So temperature is changing here. Generally, this modified Bernoulli, they won't ask you anything more complex than this. They have to keep it simple. Because it will become too messy after that. There are just too many variables. But this is easy to solve. This is a question from Meredo. Think how to do. I hope you remember the Bernoulli is modified. I'll show you in case you didn't write it last time properly. P plus rho gh plus half rho v square plus internal energy per unit volume is constant. So you take 2 points, one inside the hole and one outside the hole. And curve. Abhi, what you have to do from there, think. Give it a try. Just give it a try, get some water and come. Yep. See how to do this thing. This is slightly complex. Most people feel it doesn't have enough data. Number of moles are not given, pressure is not given, nothing is given. So let's say when this guy is flowing out, let this point be 1 and let this point be 2 and let the speed be v. And inside, right, speed is 0 because the flow rate is 0. So when you apply the equation here, we are using the term P1 rho gh1 half rho v1 square plus internal energy u1 by volume v1 P2 rho gh2 plus half rho v2 square by internal energy u2 by volume. This is 0. Why? Vacuum. This and this will cancel, same height. This is 0. We neglect the flow rate. This is 0. Why? It is vacuum. Internal external temperature is 0. You're just left with P inside plus internal energy ka formula is how much? F by 2 nRT. Hope you remember. By volume is equal to half rho v2 square. This will be P into volume by F by 2 nRT by rho by 2 into volume is equal to v2 square. What is PV? PV is nRT, na? PV is nRT plus F by 2 nRT. What is rho into volume? Mass. And 2 goes up. This is your v2 square. So we get v2 is equal to root over 2 times nRT 2 plus F by 2. What is mass? Mass is nothing but number of moles into molecular weight and gets cancelled. So V2 will be RT 2 plus F by 2 by molecular weight. I gave you a more general solution. You can prove it even for oxygen also. Oxygen ke liye F will be 5, molecular weight will change. For helium, F is 3 and molecular weight is 4. Substitute there, you got the answer. R is a gas constant, you know everything. Generally, right, when this question is given, people don't understand how to approach this. The problem is they don't know the modified Bernoulli. If you try to apply Bernoulli, sir, you suddenly are confused, like how do you apply, like people don't realize the temperature is changing, you have to account for that. Have a look at this. So if you see, right, velocity of efflux may how many varieties we did.
So why do we neglect flow rate?
Because if the inside also starts flowing, na, ye we calculate nahi kar payenge. And dusra, it's a very small hole, right? We are assuming little gas is going out. It's all because of that small hole we can do that approximation.
Sir, at absolute zero, we consider the velocity of gas particles to be zero, right?
No. Gas particles, na, question is find the velocity of the gas coming out of this. Na. After going to infinity, it will be 0. But the question is velocity of the gas coming out of the hole. If you leave it like that, eventually all the gas will go to infinity and 0 will come. Oh, alag story hai. That is why, na, we are writing internal energy is 0. All clear with this?
Yes, sir.
This is a good one, right? If you see just on velocity of efflux, right, the thing we can manipulate so many stuff. Clear? Let's say we have a container here. We have a hole here. You place this on a smooth ground. Density is rho. Area is A. Height is H. Okay? Sealed container. So water will come out, right? So when the water comes out, isn't it looks like a rocket car thruster? The water jet is flowing out, so it will push the container, right? Find the initial acceleration of the container. The moment you open the hole, water will come out, pushing the container backward. Find the initial acceleration of the container. How do you do that?
Sir. So you give small area and its value also. So while finding velocity, we have to count.
I said small area only, no? Matlab we have to take root 2gh only.
Okay.
What is the catch? Do you guys remember this water jet formula?
Yes, sir.
So if your water jet is going this way with speed v, area small a, it will generate a force backward rho a v square. So it means this whole container is pushing back by rho a v square, and this is the acceleration. हो गया ना, एक step था question. So F is equal to mass into acceleration. So this is rho a v square. Mass is how much? Rho area total height h into acceleration. Rho cancels off. V square is root 2g h, so that is 2g h is equal to a into h. Acceleration h cancels off. We actually get a pretty interesting answer. The acceleration will be a into 2ag by capital A. It is independent of the height. Means no matter how much the height level decreases, the acceleration is constant. Is this clear, everyone? Check it out. Clear? Others can on. Clear? Next thing. If you keep on kind of, let's change. Maybe mg sin theta bhi aayega, might affect. Possible. Next thing. So that's about velocity of flux. The next thing. So P plus rho g h plus half rho v square is constant. Suppose if you take 2 points at the same height, then you get P plus half rho v square is constant. You get a interesting result here. If you observe something here, if the speed increases, pressure actually decreases. That means a fast moving fluid exerts less pressure compared to a slow moving fluid. Now don't get confused between this and the water jet. There is a catch. See what is exactly happening here. Let's say we have a container here, and let's say the liquid is going a slow moving liquid. So when we say pressure due to a liquid, the molecules are colliding with the wall. You're getting it? So you're giving more and more collisions, isn't it? Because the liquid is going slow, you have more time to collide with the wall. The number of collisions per second are high. Suppose the same thing, if a liquid started going faster, did you see the collisions decreased? So don't get confused this with a water jet, because water jet mein kya hoga na? If you go with V, you hit the wall and stop, na? The liquid is hitting the wall and stopping. Here, liquid is not stopping, liquid is just flowing. Because of the liquid flow, the surrounding the pressure will decrease. Are you getting this? That is because the molecules are colliding less and less, so the pressure exerted on the surfaces will be less. So if you think about it, this thing, P plus half rho v square is constant. You will see this at multiple places. Best example, did you ever see the calendar in the house? Think about it. If your fan is like this, and the wind is blowing downward, and you have your calendar here, shouldn't the calendar just stick to this thing? But what do we observe? Because the wind is flowing here, in this region, pressure is less. Because the speed is more.
So
And here
that
pressure is, here the pressure is more because speed is not there. So what will happen to the calendar? Calendar will fly, na? Isn't it? The calendar, that is the reason, right? The calendar is flying or the paper is flying when you have this thing. That is because, you know, the fast moving fluid will get a lower pressure region. Did you ever see this thing in local train station or metro? There's a yellow line. Now, India में तो वो yellow line कितना use नहीं है, but especially when you are in a somewhere like Japan or something and a fast train is going, what happens, right? When a fast train goes in front of the track, it creates a low pressure region because it is pulling the wind and going. So this is a low pressure region, and if you're standing here, the air behind is a high pressure. It actually pushes you towards the track. You can actually observe this, in local trains when the train is going very fast. If you put some papers or pieces of paper, right, the papers will get attracted towards the train. So things actually move. So it generates a kind of pressure there. So in football, we call this thing banana shot. I don't know whether you have heard about it. So what happens, think about it. If you have a ball here, let's say going with V and rotating with omega. So for this ball, at the topmost point, the speed is V plus R omega. At the bottommost point, V minus R omega. So the pressure P1 and P2 becomes greater than P1. Because of that, what will happen? The ball will fly like this, na? The ball actually goes in a curve. It doesn't go in a straight line. The difference in pressure pushes the ball upward direction. So this pressure becomes more P2. So if you ever seen football or played, right, when you kick the ball, sometimes you can see the ball goes over the goalpost. So same way, when you design the cars also, this especially these racing cars, let's say we have a car like this. I don't know, it looks funny, but yeah, that's a car. So now you tell me, if you designed a car like this, the air streamlines are going like this. The air is going below also, bottom also. This is V1 and this is V2. Which one should be more? V1 or V2?
V1.
So
V2 should be more. V2 should be more.
Now see, if V1 is greater than V2, what will happen? Then pressure P1 is less than P2. So यहाँ पे pressure P1 था, यहाँ पे pressure P2 था. So P2 is greater, right? So what will happen to the car? So the car gets pushed up P2 and this is P1. Car will lift off. Car will flip. Car will actually become a plane. So you have to do the same thing for an aeroplane wing so basically V1 should be less than V2. You want the pressure to push the car down. So if you take an aeroplane wing, the idea is the same. So if you have an aeroplane wing like this, the aeroplane wing is designed in such a way, the wind speed at the top and the bottom is different. So this creates a pressure difference P2, this creates P1. So using Bernoulli equation, P1 plus half rho V1 square, P2 plus half rho V2 square. The difference in pressure P2 minus P1 will be half rho V2 square minus half rho V2 square. So the force on the wing, thrust force on the wing, will be P2 minus the pressure difference into area of the wing. So this is the density of the air, V1 square minus V2 square into area.
Sir, area of wing means the area of upper and below or height.
Surface area रहेगा. जब pushing P2
Cross
into area
sectional
ना,
area,
दोनों
no?
ना surface area है. One side का surface area ना, देखो ना. P2
हाँ,
into
right.
this area, P1 into this area, right? One side का area. Got it? So the aeroplane wing works like this. So the wings are designed in such a way it generates a reverse the thrusters in the upward direction. How does that look? Did you guys see the videos I sent you?
Yes.
Look at the velocity of flux. So there we have 3 holes. Someone poured water inside. Did you observe here? See, both of them have same range. The height of the liquid above that second hole and the height of the liquid below the hole was equal. The range is same. See, it's becoming very slow. So the rate of decrease of liquid is not constant.
Dropped. Recently, some friends of mine went to the Gordon Dam
This is a dam. I
in
think last time I
Tasmania,
showed you, I guess.
which is 126.5 meters or
Big dam.
415 feet high. Then they dropped a basketball
So
over
see, so they're dropping a basketball. So first thing, they just dropped it without spinning it. Okay, if you just drop it.
the edge. You can see that the basketball
So if you observe, it is almost just falling straight. Kuch nahi ho raha hai. It
gets
is just-
pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens
So it just fell on there only. Now, if you give a spin, remember I said you get an upward thrust.
when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go! That's incredible.
So that went quite far because of that upward thrust. See how far is that? So how much it drifted?
Sir, initially it was not rotated with omega.
Initially it was not rotated.
Oh, look at
See, it
that
is just
go!
going off like a plane.
That's incredible. This is Brett who just threw it.
The basketball was subject to the
See,
Magnus effect, which
If
affects
someone is throwing a ball there, you'll observe how it goes. See,
all rotating balls or
see
cylinders
the
as
ball is going up.
they fly through the air. And it works like this. As the basketball picks up speed, air
So
on
this is that R
the
omega
ear
thing.
and golf are spin golf.
So how the ball
Could
is
have
bending inside?
non-sport
Look at this thing.
application college. But, you know, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and
See that
golf.
ball, huh? How it is going? You hit it that way. Look at that ball, how it bends inside.
But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat,
This is actually a sailboat without sails.
but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once and then it crashed. But the Magnus effect is making a comeback. Here is an experimental rotor wing aircraft which generates all its lift from spinning cylinders. And this is the E-Ship 1, which uses 4 spinning cylinders, that's 4 Flettner rotors, to increase its efficiency and reduce the amount of diesel it burns. So in the future, the Magnus effect may help more than just basketballs fly.
Oh, look at that go!
Now the real reason my
सर
Yeah.
सर जब वो कंटेनर लिया था तो उसमें एकदम नीचे फ्लो रेट कम क्यों
You can search online, right? तो अभी वो कंटेनर के नीचे फ्लो रेट, which one you're talking about? Oh, that तेरा problem वही है. You don't explain me what you're talking about. You wait
Sir.
after the class. Look at this thing. This is that this guy called Robert Carlos करके. Okay, is one of the best shots of this. You know this. It's called a banana shot because the whole thing bends like a banana. I think the video is not clear, but let's see.
Well, the way to look at the ball, look at the way he's got it. He's got it. Well, why not?
So that's 35 meters.
It's a 30-yard free kick with a 20-yard
And look
run.
at the YouTube channel का नाम है Dr. Football. And now see from the side view, it looks like it just went, but see the another view, okay? See that thing? All went that way
In an accuracy. Watch this.
and goes
That's
in.
way wide of the goal. That's 2-3 yards wide. And just
See.
clips the inside of the post. That is quite a magnificent free kick.
So it bends like a banana. That entire curve looks like a banana. That's what's called a banana shot. This you guys will enjoy. He's flying in the air. You can see a car flying at the back. There. So ever heard about flying cars? There, those are flying cars. So the problem na, normal cars will never fly. You need that kind of speed, and the normal cars are quite heavy. These cars are designed, for that kind of efficiency. So even a small turbulence or small disturbance will just flip the whole car. Clear with the aeroplane wing concept? So this is a question itself, aeroplane wing. And did you ever see the Antica nest? Whenever an ant makes, last time did I show you the Antica nest?
Yes.
So, why they build these towers actually? The reason, if you go higher you go, the more the wind speed, isn't it? If you're staying in 10th or 15th floor, you'll notice it. Open the windows and see, wind starts blowing. So what happens, right? These ants, they design the tunnel in such a way, because the wind speed is more here, pressure is less. So, and they make one more hole somewhere to the side, okay? So the air will enter inside, goes like this, and then comes out. So they use this for air circulation, because the end of the day, even ants breathe carbon dioxide. So if all that carbon dioxide accumulates, the entire nest will fill with carbon dioxide and ants die inside. So you need an air circulation. That is the reason, if you go and destroy the nest, immediately they come and try to build it up again. Not because they want to have a beautiful building. It's a air tunnel, which will maintain that air circulation inside. So generally the estimate is the depth of the nest should be equal to the height of the nest. They prefer to do that. So when you see this big hill, right, ant hill, the nest is so deep. So this actually happens, in buildings also. It happens sometimes accidentally. People don't notice it. Sometimes people design it in such a way. There is one buildings I saw. These people, how they construct a top view. The buildings were like this. Some 8 towers in a circle. Beach mein kuch ground tha. This was a design. So if you actually look at it in the side view, this actually becomes like a wind tunnel, right? So when the wind flows here, this creates a low pressure region. So the wind from the bottoms will actually start flying up. So if you go and stand near this area, right, you will find the breezes continuously blowing most of the day. You'll notice this in some building areas. There is one in Runmarg area where you'll find that. The wind is continuously blowing. Mulund mein it is there. So this was actually a technique used in Egyptian buildings when they use this thing, because it's very hot, right? Deserts. They need a continuous air circulation to keep it cool. So when you have a big house or something, in the middle of the house, they build this tower kind of thing. And if you open the door or something, wind is continuously blowing through the house. Meaning you can create pretty interesting stuff with this. So that is about the aeroplane wings. Then the next concept is venturimeter. And not only this, you can go on with more applications. For example, this though I teach for the medical students normally. Let's say a blood is flowing in an artery and there is a blockage. Generally, what people think, if there's a blockage, artery will burst. Because the liquid will flow faster, people think that way. But something else happens actually. So here velocity is more. So V2 is greater than V1. So the pressure P2 becomes less than P1. So what happens with the artery, right? Because of this blockage, the pressure outside is P0. The pressure here is P2 and P0 is greater than P2. That means this pipe is being pushed inward, right? So at some point, what happens, right? Your artery loses that elasticity. The artery actually collapses. Because the pressure outside is more than inside, the artery collapses and the blood flow stops. If this happens in the coronary artery, in the heart rate, we call it a heart attack. Heart stops getting the blood supply. You're getting it? So if you think about it, see what is happening. That is the reason. If you ever see, they keep a stent inside the artery. They don't keep it outside. You keep a stent inside the artery so that instead of collapsing, it can balance that. It can support the artery. So once upon a time, right, 70s, 80s, mein, if you have a blockage or if you have an heart attack, right, they have to do something called an open heart surgery. Literally, they used to cut open the ribs and then you used to operate on the heart. It used to be so exhausting. Patients, right, most of them used to have a lifespan of 5 to 6 years. They used to die after that. Because the entire surgery itself used to take away most of this thing. A lot of blood loss, too many complications. Then someone came with a brilliant idea. We call it angioplasty. Have you heard about it? So if there's a blockage, what they do through your thigh has a big artery, they introduce a small optical cable. Getting it? So there are two optical cables here. One optical cable will shine light, another optical cable has a camera. So this will shine light and the camera will record what is there. On top of it, there's a small balloon here, one more pipe. So this is pushed through the arteries till the blockage. So once the blockage comes here, right, they pump air and they inflate a balloon. The balloon will push the blockage. You're getting it? They will push this thing till where the blockage is there. And then they pump air inside and यहाँ पे एक corner में एक balloon है. When you pump air, this balloon will expand, pushing the blockage. That is how they remove the blockage. There is no need to cut anything open and the operation is done in an hour or 2 hours. You can go back to work in the evening. Just a small cut on your thigh, done. So, and if you think about it, someone actually thought about it. Why don't they use, and the guy who thought about it must not be an engineer. He must be a doctor who had some knowledge about physics. Maybe who had some knowledge about recent developments. If you see doctors ka wahi problem hai, most of them are not updated. If you ever go to a hospital, right, and you have to get a surgery done, never go with an experienced doctor. Matlab, you should not go with anyone more than 10 years experience, not anyone with 2-3 years experience. Somewhere 6-7, this guy is a sweet spot. Because someone with more than 10-12 experience, what will happen? He will become the hospital director, right? He'll be in a big position. A guy in the big position, what he will do? He'll do administrative work. He is not doing operations recently. The guy 1-2 years old is too new to learn. He'll be doing mistakes. So generally, if you see these people, when they go to the hospital, they ask like, I want the senior most surgeon in the hospital to do surgery on me. That guy might have 40 years experience. Outdated models, outdated techniques. He must not be doing surgeries only recently. So there, people just don't realize it. So just because, you have a lot of experience doesn't mean you will do quite well in that. You have to keep updating. The doctors don't do that most of the time. So that is one of the issue, but that is irrelevant for you guys now. Next thing, venturimeter. Just have these few series left. Let's finish it off. Chapter is almost done. You can finish a full HCV now. So what is this venturimeter? This is especially useful, to find the volume flow in a gas pipeline or something. For example, Russia sells gas to Europe, used to sell. Maybe it is selling, but they blasted the pipes. That's a different story. How does Russia know how much gas went through the pipe? It has to put a bill, right? In your house, you have this gas meter, right? How does the meter know how much gas are you using in the stove? So we use something called a venturimeter, which is useful to find the flow. So let's say when a liquid is flowing here, so let this height be h1. Let this height be h2. So from here to here, if you see, this gap is delta h, the height difference. So here velocity is v1, pressure is p1, velocity is v2, pressure is p2, area a1, area a2. So venturimeter ka questions, right? Generally, they'll give you some 3-4 quantities. They'll ask the other one. So first thing, equation of continuity, a1 v1 is equal to a2 v2. Next thing, Bernoulli's equation at 1 and 2, P1 plus rho half rho V1 square height is same. P2 plus half rho V2 square. And what is P1? When you take the pressure from the topmost point here, this is P0 and P0. P1 is nothing but P0 plus rho g H1. P2 is P0 plus rho g H2. So from here we get delta P, which is P1 minus P2 is rho g H1 minus H2. Substitute here, we end up with P1 minus P2 is half rho V2 square minus V1 square. This will be rho g delta H is half rho. So from here you can find the speed V2. And we also know A1 V1 is equal to A2 V2 now. So V1 is equal to A2 V2 by A1. Rho cancels 2g delta H. V2 square by A2 square, V2 square by A1 square. It's simplification basically. So V2 will be 2g delta H by root over 1 minus A2 square by A1 square. Root. Just looks like velocity of efflux if you observe. Isn't it? Looks like velocity of efflux. So this is a venturimeter. So this is the theory, this is the concept. Then this is one venturimeter. Venturimeter, there is an alternate version. We call it a manometer is connected. In this, the venturimeter looks like this. In this case, there is no openings here. These two are connected together. So here the liquid is flowing. Here we use mercury here. So we have two different liquids here, the mercury and the liquid here. Let this velocity be V1, pressure P1, area A1, V2, pressure P2, area A2. Let this this entire thing is filled with liquid. Density of the liquid is rho L. Density of mercury is rho mercury. This difference is delta H. Let this be X. Same stuff. Equation of continuity, all these things, the same story you write. P1 V1 is equal to A2 V2. Then, if you look at this point here, A and B, pressure at A is equal to pressure at B. That is nothing but P1 plus rho liquid G. I'm using that vertical thing, delta H should be equal to P2 plus, do one thing, don't take A and B here.
So means you're writing the condition for equilibrium.
Write A and B here. Better. That will be on the right side will be P2 plus rho liquid G X plus rho mercury delta H. This and this term will cancel. We end up with P1 minus P2 is equal to rho mercury G delta minus rho liquid G delta H. Then equation of Bernoulli equation P1 plus half rho V1 square is equal to P2 plus half rho V2 square. Three equations, right? You'll get whatever you want. They'll mostly ask you find V2 or something. So this is the same as the previous one, but in this case, the venturimeter is like this.
Sir, How does the Venturi meter, how does this whole algorithm help to like calculate how much of the
So-
fluid is used?
Basically, I can find this velocity, right, at any point. Let's say I can find V2.
Yes.
So first of all, this difference in mercury level can be measured. Let's say वहीं पे कुछ sensor something is there, and that will give you the voltage difference, which will tell you the height of the difference in height. Once you get delta H, from there I can find V2. Once I know V2, A to V2 will be the volume per second, na? हो गया ना? I'll know how much volume is flowing every second.
Oh,
Multiply
okay.
into time, then I'll get how
Uh-huh.
much volume flowed.
Right.
ना? Because if यहाँ पे देखो ना, V2 में सिर्फ delta H में आ रहा है ना, ये delta H तो measure कर सकते हो ना? The last concept, siphon. Siphons were quite famous when I was in school.
Sure.
People used to use it a lot to steal petrol. Sorry, bolo.
Sir, in that manometer, sir, PA and equal to PB can only be when both sides.
Equilibrium. वो नीचे steady state में है, नीचे वाला liquid.
So both side when liquid is same, then only it can be.
नहीं ना, हाँ, तो ये point है, point भी same liquid है ना?
हाँ, मतलब पूछ रहा हूँ कि अगर नहीं होता तो
Yeah,
same.
yeah. Same liquid नहीं होता तो you can't do that. Same liquid होना चाहिए.
Okay.
Then this Ventimeter का one recording रहा है.
Sir, the second term you wrote for because of the pressure of that water liquid.
Come again? Yeah. So what's the siphon here? This thing, right? Quite a useful concept. If you have a pipe and you want to pull out water from this thing. When I was in school, right, 5th or 4th standard, we didn't have this running water. Water सिर्फ आता था morning 1 hour and evening 1 hour. So what we used to have a big tub. Okay, and the tap is there. So when the tap comes, it just fills up. So I, being a small kid, right, 4th or 5th standard, abhi bucket se pani chahiye, so I couldn't take it. So we used to have a pipe inside like this. So I used to put my mouth and pull the air outside. So once the entire air is removed, the water will rise, and the water comes out continuously. Once the bucket is full, I used to put the pipe back in again. So you can pull the water out of that thing, right, without using any external thing. Best example, if you go to air salon, they use that sprayer, na? That thing, that's actually kind of based on that. When you're pumping it, you're creating a vacuum, liquid rises and gets sprayed outside. That's actually kind of siphon. Getting it? So how to use this to steal petrol? There's a bus there at rest. The driver went down to do something. You go there, the petrol tank hota hai na, this thing, you break the lock, put the pipe and pull out the petrol, fill up the bottle and run away. So in my entire area, right, people used to park bikes and vehicles outside. Na? Night thieves used to come and steal petrol from all the vehicles and go. यही करते थे. So siphon gang.
Sir, but step 1 we have to blow out all the air.
Blow out nahi, you have to pull out all the air.
Yes.
So by chance sometimes petrol goes into your mouth, you have to be careful.
Okay.
So yeah, let me show you how that looks. Not exactly stealing petrol, but yeah, applications, practical applications.
This siphon, the upper.
First, let's see how this looks, and then let's see what is the working behind it.
This is a working siphon. Unaided by any machine, liquid is moving through a hose from one container to another. The forces driving this process are complex and interesting. Let's investigate. Start by sitting a cup full of water on a block and an empty cup on the table. Position a hose so that it connects both cups. I colored the water to make it easier to follow this process. To start the siphon, we need to fill the hose with liquid. To do this, insert a pipette into the hose. Squeezing the bulb forces air out of the tube, creating bubbles. Slowly releasing the bulb, we see liquid moving into the tube. We might say that the pipette is sucking liquid into the tube. Actually, the liquid is being pushed into the tube by the external air pressure. When we released the bulb, a partial vacuum appeared. External air pressure pushes water toward this vacuum. To start the siphon, remove the pipette while holding the end of the tube below the level of the liquid. It is important to keep this end of the tube below the liquid level, or the liquid will run back into the upper cup. Once started, the liquid will continue to flow.
So if you see the logic behind it, right? The left side ka potential energy is more than right side, right? This is the liquid is going down as long as the potential energy is same. In chemistry, we call this activation energy. If you think about it, even though the products are having less energy in the reactants, liquid won't go automatically. You have to provide initial energy for the reaction to proceed. So pulling the air out is like providing that activation energy for the reaction to happen. Oopsie.
This is a working siphon. Unaided by any machine, liquid is moving through a hose from one container to another. The forces driving this process are complex and interesting. Let's investigate.
So that's a siphon.
So it will go on till both levels.
Till the heights become same. Because once the heights become same, there's no change in potential energy. There's no need for the liquid to go on.
Sir, if that container with full liquid is kept on the same height as the empty container, then will it?
Then half the height, no? That will go till half the height. Both will become h by 2, h by 2.
So, but no one is having difference in potential energy.
That's why it will stop flowing now after once the heights become equal.
No, sir, means in this case, he kept a block on that, he kept that jug, na? But if we remove that block and keep both the jugs on the same level, I'm telling you.
Height of the liquid is not same initially.
Okay.
Once both the heights become half and half, it will stop. Initially, left side में height ज़्यादा था, right side में पानी है ही नहीं. You have to see height of the liquid surface, height not height of the table.
Okay, okay.
So here, if you see now, the liquid will flow
look?
from here. And comes out like this. So if I call this point 2, and if I call this point 3, if you look at the heights here, this is the height h2, this is height h3, and this is height h1. So what are these heights exactly? h1 is height of the liquid from the height of the liquid surface. That's not height of the container. So if the liquid is going down, h1 will decrease. h2 is the height where the liquid exits. h3 is the maximum height. In the entire siphon, the maximum height of the process. Now, if you apply Bernoulli between 1 and 2, we get P naught. The height is rho g h1 plus half rho v1 square. The area is big, so we can neglect it. P naught, height is rho g h2, and the velocity is half rho v2 square. P naught cancels off. You get v2 is equal to root over 2g h1 minus h2. If you see, all the answers look like siphon ka answers only. So the root 2gh is the difference in the height. So this is the speed which the liquid comes out. So once the height of both the surfaces become equal, that means once the liquid level becomes this height now, meaning assuming the pipe is there till here, once the height reaches this here, the water will stop flowing out. Now, in this, there is one exception though. If you apply Bernoulli between 1 and 3, something else happens. P naught plus rho g h1 plus half rho v1 square. Or between 2 and 3, we can do actually. Pressure at P3. Height is rho g h3 plus half rho v3 square. v3 is equal to v2 because the area is same. you end up with P3 will be P naught minus rho G H3 minus H2. Pressure should be always greater than or equal to 0. So we get H3 minus H2 should be less than or equal to P naught by rho G. P naught is 10 power 5, density of water is 10 power 3, and 10 approximately 10 meters. Look at this thing. What is the meaning of this? If the difference in height is more than 10 meters, liquid won't go up only. Where did we see this thing? Barometer, we learned this thing if you remember. So for water, what will be the height of this thing? In this formula which we used, if I use water, what will be the height here? 10 meters, right? Iska meaning kya tha? In a siphon, even if you create vacuum, what is the maximum height the water level can reach? 10 meters. So by chance, let's say if you make a siphon like this, where the height is 11 meters, kya hoga? Water will reach 10 meters and stop, na? Water won't go only. Got it? Did you ever see these hand pumps? Hand pumps work only for a depth of 10 meters. Because hand pumps work on the principle of siphon. Because even if you create vacuum, water can't rise more than 10 meters height. So you can't pull underground water more than 10 meters deep with a regular hand pump. So the kind of motors we use are differential pumps. They have a totally different concept. Is this clear, everyone? Siphon is the fourth concept. There. So in fluid mechanics, we have 4 things: velocity of flux, aeroplane wing, siphon, and venturimeter. So with this, we're done with fluid mechanics. HCV, there are 36 questions, I guess. Finish off examples, objective and objective and exercise. Make sure to do examples and objectives. We have done almost like 38 problems, I suppose. Yeah, you can go through them once. So tomorrow there is no class, right? We are directly meeting on Wednesday again, 8:45 as usual. And next Friday there is no class. But Saturday will be there a class. Right? So in case you're planning something, plan it out. Because actually next week, the pace people I gave all off. I have only your batch. And I'm going to my hometown. I need to spend time with my mom. Or else she's going to kick me right and left. Because she's already pissed off. Like you said, you're coming for vacation and you're taking classes. So I was convincing her, nay, evening, late night classes, morning, we can roam outside. So yeah, so Friday, so tomorrow we're not catching up. So let's catch up on Wednesday. We'll start with something called viscosity. Small chapter, not much. Mostly we can wrap up viscosity on Wednesday only. So we have small chapters, viscosity, and then we have, where did they reach in pace right now? Viscosity is finished. They didn't start.